Alrighty, so let's go back to the Canvas shell just to make sure we have everything properly set up. This was the Zoom recording from last Friday's morning session. It was pretty much the afternoon session, so I only recorded one. You put in that link and then you would enter in that code. All right. Last time we started over talking about signals and their, delta, ramp, and step functions, and delaying and scaling those. And I do have some notes that you guys can read. And they're in Google Docs. And you might think of these more of a lesson plan. But let me scroll all the way down. Right, so where I actually put an exam-like question, and I give the answer right here. Also, you should be able to get, if you click on it, you should be able to download the Python code that I used to create it. And pretty much every figure should have some Python code associated with it. All right. So that was last class. This class, I decided to try that again. And so there's some notes for module 3, which I have here. And it's like things we're going to go over, and pretty much any figure should have some Python code with it to go with it. And we have 3 more homework assignments. We're going to draw some what we would call advanced signals. And this homework assignment, right, you would do on paper or electronically, right? And then scan your document and upload it, right? And you can check your work with Desmos or Python or however you want. And then when after the due date, I make the solutions available. Today we're going to go over continuous or discrete, what that is, and that is a My Open Math assignment, which is multiple choice. You can do it as many times as you want until the due date. We have another My Open Math where you're given a function and you write it out, and then you see various things, and you have to write the equation for what you see. You should be getting like randomized problems for that. Now, what I wanted to point out something. just to see where we're at. All right. I've kind of outlined the midterm already. And so, like I said last time, sample question 1 is really something like this, and you have to tell me what it is. Okay, that's pretty good. But then there is another plotting program problem buried in here, and it's something called convolution, which we'll go over later. But essentially what convolution is when you take a signal like a step, a ramp, a sine wave, and you put it into a system, and then you mathematically find what the output is. And so most people have no trouble coming up with the equation, right? But you're supposed to plot the equation, and that's where people fall down a little bit. So that's like an implied task of that problem. And in fact, so even though we are on kind of still on some signals and we haven't done convolution yet, in fact, because we're still plotting things, we're actually, in a way, starting part B of question 2 on the midterm. So starting with that, let's plot f of t equals RT minus ramp t minus 1 minus ramp t, t minus 2 use that color, plus ramp t minus 3. Okay, and just as a quick review, right? The ramp t function is times a step function, and it gives us a unit step upwards at time equals 0. And if I were to delay this, right, by 1, that'd be r t minus 1. And then I could scale them downwards. All right, let's do the first ramp. And let me just rearrange the scale there. So RT gives us a slope of 1 at time equals 0. And remember, it keeps going on forever. Can't draw forever, but that's what it's doing. Then we have this light blue, and at 1, it's going to be going down And then we get the same kind of structure. At 2. And then we get an upwards plot at 3. And so the key thing with ramps, right, is in fact, we're just keeping track of the slopes. So we're going to have a positive slope, then it'll flatten out, then we'll have a negative slope, and then we'll have a positive slope. So if I just write the slopes here, +1, -1, -1, +1, you should be able to see what's going on at any given time. So 0, 0, 0. Only the first ramp is active, right? But then at time equals 1, the two slopes cancel out. Then at time equals 2, it'll keep going down. And it would do this forever unless we added this last slope back in. All right, and that means we have a trapezoid. So that was a lot of review in 12 minutes. Are there any questions?
Yes. Do we?
Hold on a second. I might. Okay, can you repeat your question?
Did we go through sinusoidal functions earlier?
Regular sines we did during the review. Okay. And the thing is for midterm 2, we're really doing non-periodic waveforms, you know, things that don't repeat in time, because well, the way the Laplace transform works, which is what we'll be working on, every waveform is multiplied by a step function. So we don't use that so much. Although on the Bodhi plot, we use sine waves, but we don't necessarily draw them out, like delaying and scaling them. And what I do is the delaying and scaling that is done of a sine wave, I show you right when you need it. Okay? Does that make sense?
Yeah, it does.
Okay. Now, you know, if you really can't wait, well, you know, make an office hour appointment and we can chat about it. But the, yeah. Any other questions? Okay. So we will be doing exponential functions pretty much the whole semester. All right. And there's two kinds, really. All right. we assume everything is in time. So when we say decaying exponential, right, as you have positive time, the exponential decays, right? It gets smaller, right? And an exponentially increasing in time is plus t. Now, we actually do talk about both of these, but this one, where you have exponential increase, it's not a very good technical term, but most often that's considered bad, where something is not working in a controllable fashion, right? Let me think of an example. Because what happens is you put in any input into a system like this, and it just kind of goes through the roof, if you will. Well, I'll just leave it at that. Now, at time equals 0, right? You know, for negative t's, it does increase, but we're going to change. We're going to actually modify that with a step function. All right. So the question is how core processors have reached a limit in growth. That's very interesting. Because what you would have is a system and you would have your inputs, right? Now, when you talk about core processors, right, maybe what we're measuring is number of cores per die, right? Before, maybe it was transistors per chip, but now it's like, you know, how many CPUs do you have on a die, right? So if I have my inputs, right, over time, right, those number of cores are going up, right? Now, just about like with anything, not that I'm giving stock advice or anything, eventually we might hit a limit, right? Which is, which means there's something in this system that would make it kind of even off, okay? So, I mean, myself, I was thinking really of, we all have parents that have things that if we talk to them about it, they're going to really go off, and you're not going to be able to calm them down after you bring up a topic, right? So that was just my simple example. But Fernando, I like your cores example better. Okay. But yeah, we will be talking about systems and signals and circuits. And so a lot of EEs do well in management and they get their MBA because we think about things in systems. The systems we talk about are linear, time invariant. And unfortunately, life is not linear and it's not time invariant. Now, you might think that's just a bunch of dad humor. I'll explain what a linear time invariant system is. I think it's 2 lectures from now. All right. But so we have e to the minus t, but we will, we can have a scale factor here. We have e to the minus t, but we multiply it by a step function. And we're going to find that for our analysis tools that we use, everything is multiplied by a step function. All right. So, just at t equals 1, t equals 0, e to the minus 0 equals 1. That's easy. All right. And then you might recall there's something called tau, right? So e to the minus t would be e to the minus t divided by 1. And it takes 5 time constants approximately to get to 0. And what that means is e to the minus 5 times 1 divided by 1 is e to the minus 5, which is very close to 0. So I see the chat. I'm just going to relabel this graph. 1. Okay. And it takes 5 tau to approximately get down to 0. Okay. Hey, Fernando, I just saw your chat about what you meant by size. And yeah, I was guessing which way to go. Size, there's also power. There's many things to evaluate a core processor on, and I just made up one. But size is certainly okay. And then to read Juan's message, are we talking about our RC time constant? You better believe it. We are just doing a plot, right? But this exponential decay, right, is something that real analog systems have. All right. Now I can do any shape I want kind of digitally in a system, but for a real analog system, everything is exponential decay. So just some things to remember, right? If I have e to the minus 5t, right, ut, then I would have u is the same as t divided by 0.2. Tau is 0.2. 5 tau is 1. And so I would decay a lot faster. All right, looks like the chat's filling up. Oh. No, it's so yeah, about my I think my internet's pretty good. I upgraded during the spring, maybe just like everybody. But so to answer Brandon's question, does it always take exactly 5 tau for the exponential decay to reach 0? That's a pretty good summary. The professor in me would say to reach approximately 0 or effectively 0.
I believe he meant to refer to a static state. What's he talking about?
I'm sorry, could you just slow down a little? I didn't quite catch that.
Was that, I believe, was called a static state. Was it
Static state?
the period he's referring to, the 5?
That's just
the one you were just talking about.
Yeah. So what I'm saying is 5 tau is how long it takes to go down to 0 for an exponential decay. If that didn't answer your question, I think I'm having a hard time. Maybe just put it in the chat and I can see it maybe a little better there. Okay.
It was basically the same thing as Brendan, someone already put down earlier at 3:23 p.m.
Okay. All right. So there. Okay. I'm just going to move on then. Now, we can also delay these. So, but if I'm going to delay by a second, I have to delay the step function as well, right? And then I put in the time and whatever delay or shift I had here. All right. And so what that does is it delays the whole thing by 1 second, right? And again, it's a little hard for me to draw decaying exponentials. All right. So if you want a lot of examples, all right, that's what the notes are for. And you can see here's all the decaying exponentials. You probably have to zoom in to see some of that a little better. This is more for you after class. You can see how they're exponentially increasing for negative time. You have a step function, you multiply them together, and you get various discharge rates. I did a quick table for the various taus. All right, so if tau is if alpha is 1, then tau is 1 second, and 5 tau is 5, and you can go from there. Right. You can also, and then here's the shift where I shifted things by 2, and you get that. All right. Now, yeah, for the final thing, we have a shape that you might see on exams. Okay. So in fact, this is a composite function. I've just pulled out the UT, right? I have a UT minus UT e to the minus alpha t. All right. And so, yeah, this is exponential approach. And that's my exponential approach. And yeah, it takes 5 tau to reach approximately your final value. All right. And that would take 5 tau is about 1, and then that would do that. Okay, let me check here. Okay. This is alpha, and it's just a scale factor. And eventually, instead of alpha, we're going to use something called omega naught when we start getting into the frequency domain. All right. So I'm going to pop back to here because the drawings are that much better. All right. So here's an exponential approach, and you can see that as alpha gets larger, it decays faster and faster, or approaches faster and faster, right? And then here I delay it by 5 seconds. So I have to delay the step, and I have to delay the exponential. But here's the thing, if you take this shape and just redraw it 5 seconds later and upside down, it's the same thing, okay? Yeah, it's called notes. Just maybe I'll come up with a better name. But if you come to module 3 and notes, that's where it is. Okay. Maybe I should say Google Doc Notes or something like that. But thanks for everybody who pointed that out. And so here we have we have two functions happening at time equals 0, this exponential decay and a step function. And then here we have another step function and another exponential decay. And we're kind of getting a square wave eventually. But this equation, right, is something you might derive as part of question 2. And then you would have to plot it. And as I risk of repeating myself, most people are able to find the equation fairly easily, but then they kind of get a little bit lost in the plotting. I'll give some hints about how to do that when we actually get to convolution. All right, let's think about that. So in this case, so the question is, what happens when alpha approaches infinity, right? And what we can say is, and so that means that this term goes to 0 faster and faster and faster to the point where as if it was, if this were just 0, right? Well, then 1 times step would be step. So the question was it 1? Yeah, the question from Juan was, as alpha increases, do we get closer to a step function? And yeah, as alpha approaches infinity, this term just drops to 0, right? Because I'm not really setting t to infinity. So t is some finite number, right? Some finite number times infinity, right? When you raise that to the minus of that product, you get 0. Okay, great question. Now, what I wanted to do is actually go over a little bit of the the integration part that I'd prepared. Okay. And then finish off with analog versus digital. All right. And what these equations are just examples, right, with the answers. And that it'll give me an idea of what to cover. But this could almost, if you took a subset of certain things, it could be like a study guide. All right. And then there's integration as time. But before we move on, are there any questions about that? Or I mean, those notifications. All right. Now this relationship, it's like a definition, right? And we could also say this. So if that's the delta function, and I have A, B here and B here, and they're just this side of 0, and then I take my integrating process and integrate over this infinitely thin and infinitely high, or 1 over infinity thin and infinitely high shape, that the area under that is 1. Okay. So even if we shift this and we integrate over all possible time, we still get 1. Okay. But A now has to be less than 1, and B has to be greater than 1, right? So this equals 0, right? Because I'm integrating from here to here, and it doesn't overlap the delta function, and so I get 0. Thank you. All right. So now we're starting to see that when we integrate over, all time, we'll always get one. If we have finite limits of integration, that it has to overlap. Otherwise, we get nothing, right? So this definition, relationship comes out of the first, the fact that when you integrate over the area of a delta function, you get one, right? This isn't a function in time. It's really, this is whatever this is at time t equals time, whatever, that's the value you're going to get. You're going to get a finite value. All right. So let's So again, that delta function, as shown, only exists at time equals 0. It's 0 at other times, right? The ut is 0 and then goes up to 1 right at 0. And so if I multiply these two together, right, I get the 1 that ut was, which was the original thing. So if t equaled 0, this goes to 1. And yeah, if t is less than 0, it goes to 0. So here's my sign. Oops. I want to rewrite that. So normally the delta function would be, here at 0, but we've delayed it pi over 2 to here. Okay. And so that when we integrate it, we're moving this along. And at that point, that's when they overlap and you get 1 times the delta function. And because we're integrating over it, you just get whatever the value is at that point. Okay. So all right. So now we want to integrate from here to here, right? Which you could just do, just by using the triangle rule, right? But what helps is to show you how some of these limits are changed around, all right? So in fact, I'm going to start with a lower limit of minus infinity, all right? Now, what is ramp t minus 1? Well, that's, what is a ramp function? It's really t times ut. And so in order to do this, you have to kind of expand it out. But what's t? T minus 1, right? And then we have ut minus 1. We still have infinity. All right. Now, as you know, this is equal to 0 for t less than 1 and equals 1 t greater than or equal to 1. And so we know that for time less than 1, this is going to be 0, and the integration of 0 is 0. So what we do to get rid of that step function is, instead of minus infinity, no, we know there's nothing before 1. Then we have 2. Okay. And that equals 0.5. Now, sometimes a great way to check your numerical answers is Desmos. And I've got a link there where I just wrote it out, except in terms of x. And I got 0.5. And there's a way to write a step function in Desmos where you have a sine function, which is if t is less than 0, you're -1, greater than 0, you're +1. So I add that and then multiply it by 0.5 to get the unit step function. And then the ramp is easily done by multiplying t times ut, right? You know, I even do this in my Python where I define my step and then I define my ramp right from there. Okay. And then, yeah, you can even do it in terms of t and you get 0.5. The key takeaway here is that you can have some function right? And if I want to integrate it, right, it really depends on where the limits of integration are. So if I'm calling that ft, right, right, the function exists after t equals 0. It's non-zero. So b can stay where it's at, but this case, a is less than the position a in time. It's occurring before this starts to give you any area, right? So I can change the limit of integration to -1 to whatever value b happens to be. And of course, if they're both below, it's going to be 0. And if both are here, right, well, then I just get that box. That should be enough to get you through all that kind of integration homework. All right. But now we want to do, I have a function of time, right? I have a lower limit of infinity, but now my upper limit is time. All right. And let's, oops. In order to do this, though, I have to change the integration variable to tau. All right. And I have an example of where that comes up. But in order to have a function of time, you have to have a different integration variable, and we just use tau. Now, I know that this is maybe confusing because we have 5 tau decay times or rise times, and now this is a dummy variable. All I can say is sometimes we just run out of variables. But let's just look at what's going on here, right? So if I were to integrate here, it's a function of time because I'm just getting one, right? But if I'm trying to integrate over, and come up with a parameter of time, well, notice I'm integrating, I'm integrating, right? And then I integrate over that step, right? Which gives me one. And then there's nothing to bring it down. And so I keep going. So that is, that's the step function. Right? If f or t was, we go from minus infinity to t, of a step function. Again, I have to switch to tau. Now, what is this? Well, when tau is greater than or equal to 0, it's 1. So I can replace that with 1. But the way that I enforce it to be 0 before that is now to put the 0, right? Because here, when tau is less than 0, it's 0. So then I put that 0 right here, right? And then I can get rid of the step function, although I'm not really. And this is the important part right here. Why did I just rewrite that step function? Where did that come from? Well, I wasn't just integrating t, right? In fact, if I was, right, which is, t is this, right? I wasn't just integrating that way. No, I'm into, it was that step function had no area. But then as I start to, no area, then I get a little bit. Then I get a little bit more and a little bit more, right? I know that's an absurdly large brush, but I keep adding every dt, I get the same d area, and I keep summing these little areas, right? But only after 0, okay? And so you really got to remember to put that back, all right? Sometimes I think some people it's just the fact of that, all right? Which is RT. All right, and I just want to refresh my memory of something. So I want a function of time. I'm integrating over time. That means I have to have that dummy variable, tau. but I've got a t in here, and this is going to happen. Right, so one, the integral of ut as a function of time, right, is ramp t. And the derivative of ramp t is ut, the derivative of ut is delta. And so what will happen is if I put in a delta function into a system and measure it, I can find the step and the ramp response by manipulating the output. I don't have to send in a step function to find the step function and a ramp to find the ramp. All I need is one, and then I can mathematically determine everything else. All right. So this is just like before, except that was tau. Then I delay the step function. And I can write that. Now, here's the thing. This is a parameter, and we will be using this later in convolution. All right, this is the integration variable, and then tau is time is something that we're, well, let's just say it's acting like a constant. That's what we can think of it as. So the integration of t as if it were just in relation to tau is what? T tau. And then this is oops. I apologize. Okay. So you get tau squared times t divided by 2 minus tau cubed divided by 3, 0 to t, right? So tau, when it's 0, both of those are 0. We don't have to worry about it. But when we substitute t into tau, we get tau squared times t divided by 2 minus t cubed divided by 3, which is t cubed divided by 6. However, this original ramp, right, kept it 0 due to that step function that it's made of. And since we got rid of the step function by putting a limit of 0 here, I have to put the ut back. And then I can simplify this like that. All right. This was, that's not the end of it, right? We will come back to this, but these are integrations that we'll do as part of convolution. All right. Okay, that's a great question. So what happens is, right, I can start off at negative infinity. Then I can have some function of time. Oops. A function of tau. And let's just say it's multiplied by a step function of tau, right? Well, for tau greater, for less than 0, u tau equals 0. So then there's nothing to integrate. So all I have to do is put the 0 here, f tau d tau. This becomes 1 because we're in between this range, right? So if that's minus 1, 0, 1, and this is t, right? When we're multiplying these together, right? This is what we're integrating, right? If I didn't multiply this, right, I'd be integrating this negative area and then counterbalancing it with that positive area. All right. So by putting this 0 here, it's saying whatever, this is all 0. There's no area. There's nothing. It's the whole function, right? F of t, right, which is the summation of the area. Well, there is no area until time equals 0 in this case, right? So that ultimately, whatever that integration function was, I have to multiply it back by the ut because of that lower limit of integration, right? And if I had delayed it by 1, well, then I would have to delay this by 1 as well. All right. So analog versus digital. So just a quick thing about that is that analog is like a shorthand or a jargon or an engineering term for continuous. And digital is the same kind of shorthand for discrete, except normally with a microcontroller or things that we think about, for discrete, we think the values are limited, right? You can only, if there's 8 bits, there's only 8 values it can be, but also things can only change at certain times. But actually, there's something called continuous valued, where it can take on any value, right? And discrete values are limited, right? Set by the number of bits of the system. Continuous time means it could change at any time, right? But it can change at any time, but that doesn't mean the values are continuous or discrete, right? And then there's discrete time, where things change only at certain times, but in fact, they can be a continuous or a discrete value. All right. And this table can, when you're doing the homework, should be helpful. Right. But so let's just do a few examples here. Right. Continuous time and continuous valued. Things like differential equations, right? As opposed, and that like the Laplace transform, as opposed to discrete time, right? Which is the Z transform in an EE112, right? So the output of the energy of the sun, right? It can take on any value, and that doesn't mean from 0 to infinity. It's just it can be any fractional number of what it is. And the thing is it can also take on any value at any time, right? There's no clock saying, well, now the output is this, now the output is that. Now for us, sure, as we're rotating, the sunlight gets intense and less intense, but it's changing. If you were to zoom in on time, right, you could see it changing at any time, right? Now, yeah, if you have a vinyl record and all analog equipment, right, that is continuous time and continuous value, right? I know I'm recording, and if you got to go, you got to go, right? But you can come back and finish off the rest of the lecture, okay? Sorry about that, Devin. If you're talking to your friends face to face, right, that's continuous time and valued and live music. Now, what about Zoom, right? Well, I might be an analog device, but everything is digitized by the time it gets to you, except it's happening so fast we can't tell, right? Now, what about continuous time and discrete value? Well, once I take a measurement and write it down, right, if I say that's 10.37621 volts, right, or let's just say that's 10 volts, but I write it down like it was 10 volts today at 1 o'clock, right? That measurement happened at one specific point in time, right? Discrete time and continuous valued. No, yeah, continuous time, discrete value. Another thing would be I'm just going to leave it there. So discrete time and continuous value, there's something called the switch capacitor circuit, which if you're interested in, essentially you can kind of program an analog circuit like an op amp and change the gain on the fly. All right. Discrete time and discrete valued. All right, that's any kind of microcontroller, PC, DSP, clock controls. This is really 112, right? And then discrete time, things only change, right? So here I'm just saying things are not changing in discrete time blocks. They're held. But I'm trying to draw that they can be anything. All right. And then some questions that maybe, you know, the number of students in a room, right? Is that a continuous number or discrete? Well, we're all each a person, and a person is a person no matter how small. So that's the number of students in a room is discrete, right? Now, the intensity of the light that enters your eyes while you read a print copy of a textbook, right? Even if you're reading in black and white, right? The values of intensity coming back from the page would be continuous, right? On the other hand, the output of a voltage divider, right? Those are all continuous time things, right? That's continuous. But if I write down that the voltage divider is 10 volts, and that happened at 1 o'clock, right? Well, it's discrete time because I said it happened at this time. And it's discrete valued because I said 10.0. Well, is that an infinite number of zeros? Is that 5 zeros and a 1? I have digitized that value just by writing it down. Okay. And it doesn't really matter if I use an analog voltmeter because I have to approximate it as I write it down. So in a way, even though it's an analog meter and I read off a number, I'm kind of digitizing it. Okay. And then these are those rest of those equations. So that should be enough to do the homework. Have a good day. So
yes,
I'm just gonna, all right, are there any questions?
Yes, is number 3 of the voltage divider continuous?
Huh? This one?
Yes, is that continuous?
This is continuous because I'm just saying it exists. But when I measure it and I use a finite measurement, that's when it becomes discrete valued. And then when I write it down, it becomes discrete time. Okay.
Right.
Okay.
Professor, I have a question that in Canvas homework 1D, there is no mention that I can give the exam test in multiple times assessment, only one chance available.
Is that what it says?
Yeah, it is no mention that I can give that homework.
I don't think it tells you that. You can just do it.
Okay.
All of them are set up that way.
Okay.
Because listen, if it I mean, I can check it right now. But I'm going to stop recording. Okay.